Now I'm gonna blow some brain cycles on mainly trying to understand when our little neural net here can fit a training set and when it can't. So wow, right, look at that, right off the bat, this is a training set that the neural net cannot fit. So you know, so these are training points, and there's a little square here, and like this is the input, and so it's saying this square we want to move over to the red. So we have 3 training points, and it's literally there's 0 hidden layers, so the neural net is literally computing a linear transform. And so we're kind of in the case when like we're trying to figure out, like, I guess, like when a linear system of linear equations has a solution. But I think I mean, I'm not sure in general that's something you can eyeball, because I mean, I think basically it's you do like a determinant or something, and I don't know, but we're trying to eyeball it in this case, because like this is like a small case where it's visual. So like we're trying to figure out, there should be a reason visually that the neural net cannot fit this training set. So so we got lucky, and we started off with a training set of size 3 that it can't fit. So so like okay, so here's like an idea. I will remove, assuming my app does not crash because I implemented something wrong, I will remove one of the training points. So like, let's remove the green guy. So this is saying the point 34 has to map to the point 75. And these are integer labels of 2-dimensional points, just to be clear. So I'm going to remove this guy, and then and also we want to remember these numbers, because like I'm going to, whoops, I accidentally clicked the button, but that's fine. It was 34 and 75. So now it should be able to fit this, right? So let's run it. Oh, it fits it. Okay, so now we're going to add back that point such that it could not fit it. Okay, 34.75. So why? See, it kind of seems like, it would have to pool, because like this is on the line. Is that kind of a thing? Like, So like you could postulate that like this 34 is on like a line between okay, so let's also do some manual weight manipulation here. That's not the way I wanted it to happen. Yeah, let me reset the weights and then just like try to solve it as a human. Right? Like, how would a human go about solving this? What if let's just try to fit the blue and the red. So we're going to ignore the green. I'm not going to remove it because I don't want to have to memorize what that point is. Also, okay, before we do manual weight manipulation, let's check this is a frame rate. Let's check the sensitivity of the training set, right? Okay, so like, can't solve it. can't solve it. Okay, but like, let's change. What if we make the 34 a 44, right? And then is it solvable when you do that? Yeah, yes, maybe. See that this, by the way, is the 34. I would say that is going to solve. Can't be sure, but it's like, look at the size of this weight. This weight is like 100 times larger than all the other weights. But I think it does solve it there. So reset, go back to 34, which was the unsolvable. Just double check. Yep, still not solvable. Okay, so now we're gonna try as a human. And I want to try to fit the blue and the red on their own. And so we're going to ignore the green. Going to ignore the green. And so I'm just going to switch like that. This kind of seems like it might have a property where, like, any way you do it, you have like a cross. You have two training sets that have two training points that have to cross each other. Like, is that a thing? Okay, let me finish trying to fit the situation here. So we're trying to fit blue and red, and yeah, I mean, it's kind of hard, you know, because like it's like a puzzle, you know. And let's expand this way. No, that's is it like is it possible to fit blue and red? I mean, yeah, it's gotta be, right? That's also, you can't really see it, I guess, but that's fine. Okay, so I fit blue and red, and so I fit blue and red, but yeah, and it doesn't look like green would be okay. So all right, I'm gonna go back. Okay, we're gonna remove green, and then we're gonna fit blue and red. Okay, so green is 3 to 18, so we have to remember that, because otherwise we'll never find an unsolvable training set again. This is like a good omen, because we found this training set like literally on the first roll. Okay, so this is 3 and 18. Everybody remember that? Ooh. It didn't remove the correct, my app is broken? Now I don't know what to do. Yeah, but that's not... Oh no, I broke the app. Oh god. Like, we were on a pretty good roll too. Okay, I can manually I'm just gonna manually so this is 3 to 18, and oh no, and I reset it. Oh, all is lost. All is lost. Yeah, you're supposed to, well, no. Okay, so we lost that training set, and but we also learned that my app is not correctly implementing the removal widget. I kind of just want to ignore that. Like, basically, it's kind of impossible to implement, like, JavaScript user interfaces. And, it was such a good little training set, and now it's gone forever. Let's see, do I want to... Yeah, I don't want to play with JavaScript, though, so... A thing that kind of looked like was happening was... Yeah, I mean, we want to say something like, if you have like a training set of size 2, well, yeah, okay, let's just play around with that. So, okay. So, so let's take the... the blue, what is this? Green and red. So that's 63 to 28 and 20 to 70. Okay. So it can obviously fit this blue training point. I'm gonna remove the blue training point. Wow, it worked correctly that time. And then we're gonna do like a bunch of solves, and I think it'll give the same solution every time because it's starting from the same initial conditions. Yeah, I mean, it definitely will. But, like, if we look at the solve case, you know, like, is there, is there anything that looks like... Right, so the thing we saw last time was that there's, like, this line between these two things. And so maybe if we take one of those things kind of on the line... And then for the third training point, we say we don't want it on the line. And then will that make it unsolvable? That's the hypothesis. So we're gonna say like 45, which is kind of on the line. We're gonna say let's map 45 to 0, assuming my user interface works. So we want to map 45 to 0. That's our third training point. And so it's already solved the first two, so we'll just start it from that state and see what it does, because, like, what can it do? Because, exactly, like, what can it do? So we're going to slow down the frame rate so we can kind of see what's happening. And, okay, let's see what happens. Oh, I don't think it's solvable. Maybe. No. Maybe. Don't know. Yeah, it seems like my line... Okay, I'm going to turn up the frame rate. Crank it up, boys. Yeah, we just cranked up the frame rate. Is it going to solve? I think I need to crank up the frame rate again. Maximal frame rate. Is this going to solve? I can't tell. Still can't tell. What's happening? You know what would be cool? Would be to replace the, well, you still need it for the buttons, but to add a like a, you know, like a line graph for the weights, that would actually be very cool. Am I wrong? Am I wrong? How hard would that be to implement? Because like the x-axis would be animation frame, and then the y-axis would be, you might, okay, so it does fit, by the way. Let's start it from initial condition. See, like it does fit, but like it's hard for it to fit it. So, yeah, it is kind of possible that that other training set, like, maybe it would fit it, it would just take forever. Right, we could, you know, like it could be like all training sets are fittable, except some are exponentially, like it takes exponential compute, because like you have to get the weights to be enormous, and I mean, that doesn't seem very plausible, but but anyway, let's further test that theory. So our theory is, if you have like a perfect line between two training points, target points, and then you take a point on that line and you say, you can't be on, you know, like, get off the line, then I believe it's not fittable. Because, right, that seems like a pretty good hypothesis, right? Okay, so we're going to explicitly test that. It's also like, probably, if I was like writing like math, maybe it would be more obvious, but I'm committed to buggy JavaScript implementations as a way of understanding math, and that's what I'm committed to. So like, so say like the thing that's going to 20, so we'll keep 28. I don't know why, but we'll say like 14. Now, so we want to be perfectly on this line, and so let's say like something has to go to 73. So we'll say, yeah, I guess like 26 goes to 73. And so we now have this perfect line. And so we're going to take a point on the line. Well, first of all, so like we're going to take like 55, right? Like 55 is perfectly on the line between these 2 points. And yeah, but first let's just see if it can fit these 2 points. So we're gonna fit these 2 points. Yeah, it can totally fit them. It can totally fit them. So now we're gonna take 55, which is a point on the line between the 2 target points. And right, like the conjecture, right, isn't that because like, isn't that implied somehow? Because we, like, this is explicitly a linear transform, like we're not, well, plus biases, but I think that still is linear. And so isn't it like in a linear transform, like any, you know, yeah, like something, anyway, so, okay, so we're going to say 55, which is on the line, and we're going to make it not on the line, and then conjecturally it will fail. So we'll just say like 55, but is this like the only failure case? Okay, so let's try to solve. Oh my word, I just got destroyed. I just got completely destroyed. My conjecture is destroyed. My conjecture is completely destroyed. Wow. That was rough. That was a rough conjecture destruction. What if I make it further away? Or like, let's say it has to go to 50. Right? Reset, solve. Oh no. Wow. Wow. Just got completely humiliated. Listen, here's the thing. Like, okay, each of these weights, has like a very interpretable effect, right? And they're like, the effect is independent of like all the other weights, right? So like this weight scales along the x-axis, like independently of any other weight, right? Like you can do that and it still scales. So you have like a scale, you have a shear, and then you have a bias, which is a translation. And then it's completely analogous for the y-axis. So it seems like if you have a training set of size 2 and you have fitted, you should be able to find like a third training point that, for which there is no path of, like weight manipulations. Right, because like you can interpret the thing as graph search, right? Like every point you have these, or I guess like trees, or, like you have 6 actions available to you. And so it seems like there should be, yeah, but it seems like there should be instances like where you have fit a training set of size 2, and there are no actions available that will fit like a particular third training point, like whilst maintaining the other 2 training points being fit. Because like in the case with 2 points, it's, yeah, like you can always kind of like fit one of them. So like let's fit the red point. Okay, so like we've successfully fit the red point. And then it's like you always have like compensatory actions. Like, so if I want to fit the green point now, it's like, okay, so moving it over, and I'm also moving the red, but I can compensate for all the moves that I just did with the red to keep the x coordinate fitted, and then you can do the same with the y. Like, right, and then I can compensate for what I did with the y. Right? So you have like a theory of compensatory, right? It's like you fit one point, and then to fit the other point, you're going to mess up the first point that you fit, but you always have like compensatory actions for the first point. And so then it's like if you add a third point, right, like clearly at some point you're going to have too many points and like you can't fit it. So like here, is there some third point that we could add that would render like no compensatory actions available? It's also like the x and y dimensions are independent, I believe. Yeah, so it seems like, right, I mean, like, just eyeballing this, right, like, it looks like if you say, like, hey, what about if 5, you know, has to go anywhere else? Won't that mess it up? Let's say 5 has to go to 90. And, yeah, solve that. Oh, it solved it. Oh, no. Okay, what about if 5 has to go to 0? Yeah, it looks like it's... But you can kind of see, like, it's already solved on the x-axis. Like the x points are correct already. So it's like, can you solve any configuration of x? Like, if we just focus on the x-axis... Let's just focus on the x-axis. Okay, so if I say, like, you know, 21 to 28. Okay, now you're not going to be able to see the training sets because of interference with the other lines, but that's fine. So, like, 21, 28, and then, like, 41 goes to 43. This shouldn't be solvable, you guys. And then what about, like, 48 to 47? This will definitely not be solvable. Oh, it's easily solvable, never mind. Yeah, the whole shear. It does a shear there. What if I say this is 61? That shouldn't affect anything, but... Yeah, that didn't affect anything. Is anybody giving me the answers? No. I was just checking. Oh, okay, here's one. I just came up with one it probably can't solve. So, say like 25 to 29, right? Like this is going to require expansion. So say 23 to 20, right? Like that requires, like you have to expand to fit it, right? There's no other way to there's no other way to fit it. Also, let me make those even, just right. The only way to fit it is by manipulating this weight. Right, that weight has to go out. Right, that has to expand. That's the only way to fit it. So if I run the fitter, it's only going to do this weight broadly. Yes. Yes, that is correct. So then, we just find a training set that, or we add one more point that violates that expansion, right? Like we add like a compression point. That seems like it should. So like, compression point, but like, yeah, I don't. I still feel like it's not gonna work, but I mean, like 72 to 77. I don't think that's going to do it. Yeah, because it can shear. Yeah, I mean, it can shear and expand, so that's fine. That's not. Well, okay, you could directly violate it by saying like, okay, 21 has to go to 28, right? That would have to violate it because it's on the same line. Yeah, right. Okay. So we found an instance. We have successfully found an instance of a 3-point training set that is not fittable. Now, if we can generalize this, okay. So what's happening here is we have 2 points on one row, and it requires a scaling in the x dimension, because this wants to expand out to here and this wants to expand out to there, so like you have to expand to fit those 2 points. Like you have to do this, and then we just added a third point that like counteracts that. But that's all like in one dimension. That's all like, I mean, we're literally all in one row. So like, would it be possible to generalize that to where like you're not in one row? But that's progress. That's progress. I mean, like this is a reproducible example of a training set with 3 points that we kind of have a proof is not solvable. Because to fit the first 2, there's only one action available, which is that you need this guy to go up, and because the third point like is in the same row, there's no other action available that would, although like an interesting question would be, what if we allow for nonlinearity? I think in that case, it probably would be fittable. Let's find out. So we're gonna allow for 10H activations. Oh, damn. Well, okay, I'm gonna have to main. I always forget it deletes the training set. Okay, but that's fine because I remember what it is, you know. So let's say like 34 goes to 30, right? That expands out that way. 35 goes to 39. And then the counterbalance, again, let's run it with 2 points. It's the only thing available. The only thing available is you have to run this weight. That's the only way to fit that. Like, this weight has to get huge, right? All the other weights are basically zero, except for, because we start at the identity. All the other weights are broadly unchanged. And yeah, I guess with the nonlinearity, it's going to take forever to fit that. And that's fine. So then we're going to add the third training point, which is like 31 to 38, right? Like, to fit 31 to 38, you have to do the opposite. Like, this weight has to go down instead of up. And since the other two require it going up instead of down, it's unfittable, at least in the linear case. Now in the nonlinear case, I don't know. Like, it actually still looks like it's not going to be fittable, but it's not even fittable in the nonlinear case. Yay. Yay. Now if we, like, but is this the only kind of, like, right, because it's like we have 2 points and it requires an increase of this one weight. But so it seems like you could generalize that somehow, like where you have 2 points that, like, yeah, like you have, like, if you could have 2 points that require, you know, like some subset of weights to be like in some particular state, and then if you could somehow add a third point that, like, would violate that state, like, the problem is you have, like, lots of different subsets of weights, like even with 6 weights. But it seems like you could develop a theory like that. You could, because I mean, any training set is going to give you, like, constraints on your weights. Listen, good sesh.